Hello everybody, this is BKC back in from the depths with another Steam Workshop Showcase. And today what we have is my Beam Engine Raft. And I originally said I'm going to go ahead and bang this out, get it out there, because there's not a lot of things really interesting with beam engines. I don't have a lot of beam engines, and I was going to just throw it together real quick and get it up there so you could have another engine wrapped on the workshop for you guys. And in the process of building this, I actually learned a few things myself, and it reawoken some more creativity in beam motors, and I ended up banging out like 5 or 6 new motors. And some of them are more beam engines, some of them are not beam engines. So the non-beam engines ones you won't see until later rafts. But we're here to check out the raft today, and it's like all my other rafts. It's not quite as in depth. I'm not treating people to download it kind of like a beginner anymore, because if you downloaded my other rafts, you should have basic knowledge of the parts. You should know how the math works. You should know about things like that. So it's not gonna hold your hand as much, but it's still like all my other rafts. And if you look hard enough, you find information in there. And we have my 2 basic beam motors. For this raft, I've basically cut everything down to a binding box size. Not really the size, more the dimensions, because the dimensions of 2 or 3 wide, because when you start getting into 4 and 5 blocks wide, you start getting into cube motors, and that's going to be all medium-sized motors. So 2 or 3 wide, and 16 long. And why 16 long? If you watch any of my other videos, because motors get most efficient when you feed them 30 exhaust in the turbos, because superchargers are stupid and turbos are the way to go, and they get maximum efficient at 30 exhaust. And 30 exhaust can be collected from 15 cylinders with 2 exhausts on each cylinder and the engine block, making the engine totally a 16. So the dimensions can be either 2 or 3 by whatever by 16. So that way it limits the designs, and I don't have to go with a hard dimension, and have motors that'll be like, well, this technically is a beam motor, but it doesn't fit on the raft because of this limitation. And beam motors can be extended out as long as you want. So this is 15 cylinders, 1500 horsepower, but I can just keep extending this out indefinitely, and I will just keep getting 100 horsepower for every meter longer I go. And the efficiency will get a little bit better in the mid-range, but it won't get any better for the top end. The top end is locked at 1288 power per fuel, and no matter how much you extend it, it will not get any better, because we are limited to 2 turbos per carburetor, and that is the max power per fuel per two turbos per carburetor. So this is our first basic engine, and shows, again, like a lot of my rafts, shows a difference to make clear that there is no difference between inlines and non-inlines. And in this particular case, the non-inlines are actually more efficient, and this just shows that a 1288 is the maximum power per fuel you can get with 2 turbos per carburetor. This shows you that 1356 is the maximum power per fuel you can get with 2 turbos and a supercharger, because the supercharger provides an extra 5% on top of what the turbos are doing. So 1288 plus 5 extra percent is roughly 1356, or that's how the game treats it, as 1356. So that's the same motors that's on my engine test RAV. And then it shows that we can extend these out, get more power, and gain a little bit more efficiency in the mid-range, but we don't. That's not really why we would do that. We would just do that to, say we needed, this motor's making 1500 horsepower, but I need 1800 horsepower. Well, you just extend it out another 3 cylinders to get your 1800 horsepower, and it would come with a little bit of a boost to the mid-range. So the mid-range might go from 793 to, like, say 950. But it really wouldn't do anything. The top end would still stay at 1356. But if we cut the motor down, say we only needed 900 horsepower, and we cut this down to 9 cylinders, we'd save some space, but we'd lose, we'd lose the power, which we don't need it. So, we're cutting it down to the 900 that we need, which is also good. But we would lose efficiency in the low end, the mid-range, and the top end, because we'd be losing exhaust. And, we wouldn't be pushing the efficiency of the mid-range as high. And the mid-range, the bottom end on this motor would be pretty close to the same, because most of it's coming from the supercharger, but it would still lose a little bit, because the turbos just wouldn't kick in as much on the low end also. So this just shows the proper way to cut down a beam motor. To cut down a beam motor, we need to collect the same amount of exhaust, and in the same space, the lowest we could cut it down to is an 8-cylinder 800 horsepower, and we're just spacing out the cylinders to get more exhaust. And it just shows that these two motors are collecting 31 exhaust, this one is collecting 31 exhaust, and since the space above the carburetor, the turbos can be laid down, we can open up the space above the carburetors and still include the superchargers and get the motor in the same space as the first one, but keep the exact same power per fuel numbers of this one, because we have the same single carburetor per cylinder with 2 turbos and a supercharger on it. So it stays, and since we're collecting the same exhaust, we get exactly the same power per fuel numbers, but at less exhaust count. So if 800 wasn't enough, we needed 900, we could still extend this out one more, and it would be the same thing as extending this out to get, say like 1800. So it's the same idea, and it just shows how to properly cut it down and how to decide between motors. A lot of times, if you have a 16 long motor, if I needed, say, 15 wasn't enough, 18 wasn't enough, but I needed, like, say, about 2800 horsepower, it wouldn't really be a good idea to extend this out to 2800 horsepower, because the thing would be like this freaking long, and it would you wouldn't have any redundancy. If a bullet came through here and snapped the crank right here, you'd lose all the power. If you put a second motor in there, just a second motor in front of this motor, you would have 3000 power, and you would still have redundancy. Or alternatively, you can get exactly the 2800 horsepower you needed by putting a cut down version of this in front of it, and just chaining all the exhaust together, and you could get the exact same 2800 out, the motor, as you'd have a full length motor, and then a cut down motor to where each one is doing 1400 horsepower, but then just collecting all the exhaust together. it's better for redundancy reasons than having just one super long motor. And then it goes into this motor, which exposes the flaw in all of these motors. These motors are 1 carb per cylinder, and to get a 1288 max efficiency, I have to have 2 turbos per carb, meaning 30 turbos. 15 carbs, 30 turbos. And in this motor, 15 superchargers. And that's because there's no sharing between any of these. You're having to repeat the parts to get the same amount of effects per cylinder. And in this motor, I'm showing how sharing can take the same core layout as this motor, which would only make 800 horsepower, to get the efficiency and get the efficiency of this motor in the same space of this motor. But through sharing, I'm able to use this low parts count, meaning it's cheap, share the parts to get the same power of the 2 most powerful motors, get the same to better efficiency of the 2 most efficient motors, and the parts count of the cheapest motor in the same package. And unless you compare between them. And then these are some new motors I don't think I highlighted yet. And it's because these motors are not the most efficient use of space. They waste a lot of along the crank. They this motor in particular, that's 16 blocks of wasted space on this side, 16 blocks of wasted space on this side. Now, if you were shoving it in a deep V along your keel, where there was just a angled block on both sides of these, it really wouldn't matter. But there's I think 15 wasted blocks of space on top, and there's still no sharing. So what I did is I repacked the cores of the 2 motors into the same 15 cylinders into the same space. Well, actually slightly less space, because I got them into 15 length. I got 15 cylinders into a 15 long binding box. So, and I got more power out of them through sharing. And so essentially this is the first motor's parts repackaged with sharing. So the core uses the same amount of parts, but since it shares, instead of making 1500 horsepower, it makes 2200 horsepower in one shorter binding box. So this is basically the first motor using sharing. And the way I did it is I used an adapter to raise the cylinder, and then I put one cylinder here, a carb there, share between the 2, and then I got one down, one up, one down, one up, one down, one up, one down, one up. And then on the front, I saved one crank spot by connecting to the adapter, laying the cylinder down, and then using the space vacated by the crank to cross over my pipe to get my 31 exhaust. So with sharing, it brought it up to 2200 power, but it's relatively the same 1288. I think it collects a little more exhaust. Yeah, it blows it away in the mid-range. It goes from 1288 to 1504, which drops fuel usage from 1.1 down to 0.7. So not only are we making more power in the mid-range, we're going from 750 to 1100 power, we're also dropping fuel usage. So this is something I just learned. I knew about it, but I just never applied it to a beam motor before. And so this is two new motors that I made. And then I did the same thing with the supercharger motor, making the same 2200 horsepower. And I think the binding boxes are, yes, slightly smaller. Yeah, 225 instead of 240. 180 versus 192. So yeah, a little bit smaller binding box. But in this motor, we went from 1356, which is the same exact 1356, but fuel usage in the mid-range, on the top end you can't really do anything about it. It makes more power, it uses more fuel, but in the mid-range we've went from 793 to 1827. So we're using 0.9 fuel to make 1500 horsepower. This motor is using 50% less fuel to make more power. So this is just the next evolution in my beam motors. I don't really use beam motors a lot, but I did apply some some of the stuff I've learned to beam motors, and repackaged these two motors, and it lets you see how I've done it there. It shows what and it also brought the density up from 781 and 625 to 1222, because not so much that space is going down, it has going down a little bit, but power has gone up, so density has gone up. And then this one goes to 9, so that's almost like a 50% increase in space usage right there. And then this is just two oddball motors that I had. I kind of call these like ice cream sandwich motors, but technically they're just beam motors flipped on their side, and instead of using everything on top of the crank, they're using both sides of the crank. But if you turn this on the side, it has the same 3x5 by 13. It's the same 3x5 by 16. It's pretty much the same as this motor, but they're still considered beam motors. And this little motor it's essentially a flat core, a singular flat core. It'd be a 1x3 core that I put two turbos on, 2 turbos per carb on, and then I think it was a 1600 horsepower, and then I was like, oh, I can get an extra 800 out of it by throwing some cylinders on top up here, where I just had this waffle pattern to collect all the exhaust, and I was like, that's really kind of wasteful. It needs more power to get the density up. So I just scabbed on some more cylinders on top of the carburetors using an adapter to get the 2 extra carbs on there, which gives me more exhaust to get the efficiency better in the mid-range, and gives me 800 more power. So that made this motor go from kind of like to usable, and nothing really special about the motor. And then this is a motor. This is one of my higher density motors that I've ever created. At 16.89, that's a pretty high density. Normally I go more for efficiency, but this particular motor happened to come out with density and a pretty good efficiency. It's a kind of a mixed motor. It's a two turbo per carb motor, which should be 1288. But it's 1302 because it's a mixed motor. The 4 carbs on the end, they see 2 cylinders apiece, and then the carbs on the side see 3 cylinders apiece. And the 4 on the outsides have room above them, just empty space. So I put superchargers on there. There's no real way to get. I could get 1 turbo on one side on both of them, but I can't get 2 turbos on both sides to get 3. So it's lower than a 2 turbo 1 supercharger per carb, but then it's higher than a 2 turbo per carb motor. So it kind of puts it in the middle. And then it's not truly series parallel. Originally the motor had extra layer on the bottom to get all the exhaust truly series parallel, but after testing it, a mixed series parallel combo actually didn't hurt efficiency all that much. I think it was over like 2,000 power per fuel, perfectly series and paralleled, but it added to the binding box so much that I think it was down to like a 12 or 13 density, and it wasn't the best motor. So the exhaust that would be trapped here that normally would go down, and I had to join them all out to bring them to the series parallel side. I think, yeah, right here. I removed all that to get the density up, and then I just fed the exhaust into the series parallel loop. So each section, I think each carb sees different exhaust. So it makes it kind of mixed, and you're not going to see the standard power per fuel numbers, but they're still pretty good. Better than a 2-turbo per carb motor, worse than a 2-turbo per carb and a supercharger per carb motor. And the way this motor really gets its power is the core layout. The crank runs down the center. It uses adapters, so you can put cylinders in a waffle pattern, and a checkerboard pattern on top of the crank. And then that lets you put a 5-way exhaust in there and collect like a crap ton of exhaust, and then another 5-way, and then feed it out over to each cylinder. And I think this motor, when you run it, it's like some ridiculous number of exhausts. It's let's look at the last one to see the maximum exhaust. Yeah, 114 exhaust gas. So it's not that the motor's stupidly efficient like I normally design. It's just running stupid amounts of exhaust gases. So it achieves like a 1777 power per fuel at 0.6 fuel usage at 29%, and that's pretty good for a 3,800 horsepower motor in a 3x5x15 binding box. So for comparison, this is a 3x5x16 binding box, so that fits in one shorter of a binding box, and it makes 2,300 more horsepower. So it's a pretty unique little motor, and if you turned it on its side, it fits in the same. So I kind of call it more like a ice cream sandwich motor, a puck motor or whatever, a 2x4 motor, but technically it's a beam motor. And then over here we have our pancake motors. When you think about it, if you stood that on its side, it's technically a beam motor that just is not taking advantage of the bottom half. I normally call them pancake motors, but technically it's a beam motor. It's a long, skinny motor. And this motor, I kind of explained that beam motors are kind of hard to get stupidly efficient, because in a small 2 or 3 wide binding box, you're limited to how much turbos you can fit per carb, and then you can do it because this motor fits 3 turbos in a single carb in a 2x2 by 2 this way, 2 this way, and 2 this way. A 2x2x2 like cubed area, and almost half of that is wasted, but you can do it. But the problem with that is, if you look on the carb, we're blocking 4 exhaust. We're blocking 4 sides of the carburetor. We can only connect on this side that the piston's connected. The cylinder's connected on, and then if this motor wasn't on the ground, we could connect to the bottom. So that limits us to 200 horsepower per carb. So if we're pushing for the efficiency of 3 turbos per carb, which is 5066, I believe, maximum efficiency, we're limiting down to 200 power per carb. Whereas in this motor, all the center carbs are making 300 power per carb and still getting that 288 efficiency. So to go to 3, we're gonna be limiting, and then this is not the most sharing. If you didn't use the regular turbos here to block, we could actually get a 4th on here and still get to 2 turbos per carb, but it starts getting really crazy because you have 2 odd ends, so something has to give. You usually have to give up some exhaust and stuff like that. But this motor right here is 800 horsepower, and it does push past that 1288 or 1356 that a 2 turbo per carb motor does, but just barely. It gets 1463 at max, so it pushes past that boundary, that limitation that 2 turbos per carb has. But it has a lot of drawbacks, and one drawback is we can only get 2 connections to the carb, limiting to 200 horsepower. But I'm demonstrating that we can do it in a 2x2 area. So we've gotten into pancake motors, which are still beam motors, and I just built a motor, and it comes with a lot of bad things. One, it doesn't make a lot of power. 2x5x12 is a lot of space to give up for 800 horsepower. The density is low, but it's not ridiculously so. In this form factor, there's no room for a crank. If I put a crank in here, the pistons would have to be on, the cylinders would have to be on top, and then I'd have to give up one of the exhausts that I'm already, I'm already losing the exhaust because it's in the a too high form factor. I'm already giving up one exhaust that counts for 2 exhausts because it's got 2 carbs. So I'm getting 4 exhausts out of each cylinder, and I've only got 4 cylinders, so I only got a maximum of 16 exhausts, which is pretty good because we're breaking the 1288 or 1356 restriction with only 16 exhausts. So there's plenty more in this motor, but without a crank, we're spending a lot of cost. We're taking up a lot of space. We're not really cost effective because we got 4 fuel engine generators, which cost 50 resources each, and I could put 10 cranks in the same spot for the same, costing the same as 1 fuel engine generator. So I could crank this whole thing out for the same cost as 1 fuel, and that saves me 150 material cost just by having a crank. But we can't do it. We don't have room for it. And then we're lacking exhaust because of the form factor. We're leaving 8 exhausts on the table, which would get us up to 24 exhausts, which would push our efficiency way higher. And there was a third. What was the third one? No room for a crank. Oh, and then the fuel. Yeah, okay, so that's all of them. The fuel, the cost. There's no room for a crank, so that drives the cost up. And we leave exhaust out on the table, which hurts efficiency. And so this motor's a decent motor, but yeah, it's got a very limited use case. The use case I say is if a lot of times when you're tiering your cannons, a lot of times all you need is 2 or 3 blocks of space for one cannon to clear a lower cannon. And so your deck, you have odd space deck heights, 2 to 3, empty space from where this cannon comes up and the cap of this one is, and then this cannon up here pops up. You might have a little narrow space 2 or 3 high, and you could put this motor in there sideways, and you could take up that space. And say if your cannons were rail cannons, say they only needed 800 horsepower extra above what your craft already has. You normally had non-rail cannons in there, and then you decided to change one over to a rail, and you had an empty space too high in between your two decks. You could throw this little motor in there to get that extra 800 horsepower, and it's decently efficiency on top of that. So that's what this motor's use case would be. Or in between, if you had some space armor that you're using for buoyancy on your ship, you could, and you needed extra 800 horsepower, you could throw this little motor in there. And this motor right here solves one of the problems of that motor. What it does, instead of putting two carbs, it uses the exact same carb turbocharger layout as this motor, but it widens it out to let it put a crank in. And by putting a crank in, it splits the carbs up. We can't get this carb to this cylinder anymore and keep this form factor. So we're giving up more space. We're going out to a 7 wide instead of a 5 wide, but we're able to get a crank in there. And since this carb can't come over here to this crank anymore, we're just adding in more cylinders. Now this does two things. One, it lets us collect 3 exhaust per cylinder, but each exhaust counts for less, because in this motor we're making 3 exhausts. We're making 3 exhausts with this carb, 3 exhausts from this carb. So when we block 1 exhaust, we're giving up 2. And since we have 4 cylinders, that's 8 exhausts on the table. In here, we're making each exhaust count for less. But since we're not blocking 1 exhaust with a carburetor, a second carburetor, we have more exhaust to be collected. So even though they count for less, we have more exhaust to collect. And this one is collecting 4 exhausts per cylinder for 4 cylinders. This one is collecting 3 exhausts for 8 cylinders, making 24 exhausts with the same 3 turbos per carb layout as this one. This one is not taking full advantage. It's able to push past the limitations of 2 turbos, but is it worth it for that extra, 180 power per fuel? Probably not. It has the potential to be more efficient, but it's not taking full advantage of it, because we have 16 exhausts out of 4 cylinders. Here we have 24 exhausts out of 8 cylinders, so we're able to push the efficiency higher because we're getting closer to maximum. And maximum is, I'm pretty sure it's maximum is 5066. But this one's just not pushing to it. We're getting about 2/3 the way there with 24 exhaust, but we're making the same 800 horsepower, but we're using more space to do it, so density drops. And fuel usage is about the same. You can sit there and argue all day whether giving up this space for a 0.1 fuel across the power bed is worth it or not. Yeah, this uses more space, but there would be less. You could need less fuel tanks. This takes up less space, but uses more fuel tanks. I would argue that both of them are efficient enough that the fuel tanks are irrelevant. So that's not really the argument. The thing is that this is taking advantage of the 3 turbos per carb more than what this motor is, and it has a crank. So I think it saves about, 100 and say, I would say it saves probably, I think I calculated roughly about 125 material cost in this motor, but it still has what both motors have a disadvantage. There's no sharing. Each car needs a duplicate 3 turbos on each one to get the same outcome, and it's wasting. I think it's this is a 12 long motor. Yeah, so this is wasting 10 blocks of space in the middle. So not only is it taking more space to do the same amount of power, which hurts density, it's also wasting a lot of that space. So this motor, it's still a decent motor. If space isn't the option, this motor's still pretty good. It's cheaper, but it wastes more space, and it gets closer to the efficiency potential of these turbos. So either one's good choice if you had that, whatever space you had. If you needed a really low form factor, this one's just taking advantage of the 3 turbos better. But it's not all that much. It drops 0.1 fuel across the entire power band, and with only 800 horsepower. So this motor, if you look at it, it has a different density. It has a different binding box size. But if you look at the numbers, the power per fuel numbers, and you compare it to this motor, it's exactly the same. And you go, well, why is it the same? Why is it making the same power? Why is it making the same maximum power per fuel? Why is it, max out the same power per fuel numbers at 100%? Why is it? And the reason is because it's the exact same motor. This is the same parts of this motor repackaged in a different binding box. And what I did in this motor, I don't think I've ever highlighted this motor yet. What it is, it's this motor. What I did was, if you saw my last video, which I filmed kind of at the same time as I filmed this motor, but you won't see them at the same time. I decided to put the optimizing video up first before this one, so you can see how I did it. All I did was I took the motor, I copied it, I cut it off, I took the other half, I flipped it 180 degrees, and then I tried to make it work, and I couldn't do it. I couldn't make it work. And what I was going to do is I was going to get rid of this entire center section and save 12 blocks of space. And I couldn't make it work. I couldn't get it to work. I couldn't get, the problem is the exhaust was here, and there was no way to get it over to the other side, and there was a lot of plumbing issues that I just couldn't make work. So what I did was I was about to give up on it and say, oh, well, this is the most efficient in this form factor, but I don't normally give up that easy, and I figured out. I said, you know what, I'm saving a lot. I'm saving actually 24 blocks of space by cutting this center out, because it's 12 blocks long and it's 2 blocks high. So what if I gave up some of those 24 blocks and just meet it part way? How part way could I get to get the density up? How much of those 24 blocks can I save? And so what I did is I flipped the other half 180 degrees, so upside down, and I offset it by 1. And by offsetting it by 1, it lets me collect this exhaust. If I wouldn't offset it, collecting this exhaust would be in the way of this crossover pipe here, and there's just all kinds of problems. So by offsetting it by 1 meter this away, I made the binding box longer. Instead of being 12 long, it's 13 long. So instead of being a 2 by 7 by 12, it's now a 2 by 6 by 13. And it was much easier to plumb up because all the exhaust collection is right here in the center. The cylinders are wrapped around the crank. They're close enough together. You can't make them share a carb to where you could get these all these half of these turbos redundant and get the binding box down even smaller. But it's able to repackage it in a smaller form factor. And when you do the calculations of binding box, this is a 168 binding box, and this one's 156 binding box, 12 smaller. Well, that just so happens to be the 10 that's up here, and it doesn't use these two adapters, so that's why we're 12 binding box smaller. We're wasting the same space here. We're wasting, pretty much wasting the same space in the same areas as this motor, but we've saved all the 10 up here, and we've lost the 2 adapters here. Or alternatively, you can say, well, the adapters are the same as you extended out the crank, but we don't use this crossover pipe and we don't use this crossover pipe, so we're essentially we're saved half of one block. And so the motor runs exactly the same. It got the density from 476 to 513. So got the density up. Motor runs exactly the same. Again, we've made this an even density, so it's no longer a center line motor. But my argument for that is it's now a 13 this way, and you'd probably put it like I said, in the shadow of a turret with an odd deck spacing. Like you'd put it in the shadow of a turret, shadowing another turret, and you'd put it this way, and it does have a center line this way. Or if you'd put it in your ballast tank / space armor, you would just tack it to the wall where it would stand up, and who cares if it has a center, because you'd put one on both sides for an extra 1600 horsepower savings. So that's this motor. Nothing really special. It just shows you the repacking of a core. And then when I was describing the disadvantages of these two motors, I got an idea. It's like, well, wait a minute. What if we took this core, because this core lacks sharing. It wastes space above the crank. This motor can't fit a crank and is really expensive. And they both use the same turbo carb layout. I said, what if I took this core and I pasted this on top of that, and I ended up with this motor, a completely new motor. And that's really all it does. We're taking the core of this motor. If you look at it, it's the exact same core of this motor. We're able to throw out the adapters and continue this crank all the way, because we don't need to collect all these exhausts and connect all these carburetors to this thing, so we don't have this weird crossover exhaust collection problem that we have on this motor. So the bottom is just the core of this motor, and the top is this motor pasted on top of it. And together, if you use these two motors, you pasted them together, you would be duplicating all these turbos, and you would be using a 168 binding box plus a 120 binding box. That'd be a 186 binding box. We're able to paste these two motors together to get the 1600 power that both of these motors would get separately, just glued on top of each other, in the same package, but we did it in a 180 binding box. So I think that's 100 and what was it, 106? No, 108 or something, or yeah, 106. No, 128, something like that, binding box smaller package. And it solved all the problems in both of these motors. This motor is expensive because it can't put a crank, and it has 4 fuel engine generators. It can't collect all the exhaust because of its form factor. It's only too high, and it's expensive, and it can't collect all the exhaust. It can't get a crank in. This motor can get a crank, but still gets 8 exhaust that's wasted, and neither one of them gets maximum potential of the 3 turbos per carb. With this, the bottom engine, all its layout problems get fixed. It's simply just putting 8 cylinders down and collecting all the exhaust, which just takes like 5 minutes to build, because you just put a whole bunch of through pipes and just go around and do add them in, and then it's being a parasite off of the top engine's carburetors. So it sees the exact same amount of carburation and turbochargers as this motor does, without all the problems of this motor. And then this motor gets the benefit of the crank from this motor, and with a crank you're able to stand up the cylinders to get the extra 8 exhaust that that motor wasted. The bottom motor still wastes 8 exhausts, and to get these 8 exhausts, I wouldn't say is worth it, because we pushed the exhaust collection over 30, which is maximum we need to get to the maximum 66, which is maximum power per fuel for 3 turbos per carb, and it shows up, you know, in the maximum efficiency being at 66% at 5714. So I think in this motor we get like 48 exhaust, I think. Let's see. There's one exhaust that's trapped that's series parallel, so half of the motor I think sees 2 less exhaust than the other half. Yeah, this one's 48 on this side. It's 46 on this side, but who cares? It reaches maximum, and I think it's like 36 or 3800 for 30 exhaust at half power or something like that. And it doesn't quite do it, but the point is that we get, if we glued 2 of these together, it'd be 4 high to get 1600 horsepower, and we'd have all the problems of both motors. In this package, we solve all those problems because the top sharing cylinders can collect all 6 exhausts out of all the cylinders, except for the back one, which has the feed in. We can still collect it, we just can't feed it in through all the turbos. We have to feed it in through only half. It gets the benefit of the crank, and the bottom engine just gets the layout super stupidly easy, and just as a parasite on the top engine for only one row on the bottom of this engine. And so it fits in less space. It makes double the power. The density's in the it's in the average range. It's dead center in the average range of my 8 and 10 that I normally try to strive for. It's sitting there right at almost 9. I think power per cylinder stays about the same. No, power per cylinder drops a little bit. Yeah, because this one's 100 power per cylinder. This one's 200 power per cylinder. So that kind of averages out. And since you have more cylinders making 100 power, it drops it down to 133 power per cylinder, but still the density's up because we got more cylinders and less space, and we end up with a really efficient motor. And then after a while building this motor, I came up with another idea which led to another motor, which is a repack. I said, what if we repack this motor for sharing? And I was like, how would I do that? Well, what I would do is I would take these carbs and throw them on top. You know, I mean, I would delete this whole half of this motor, fold this motor 90 degrees to where these cylinders could share with this carb. And I ended up with this motor. And this little motor is pretty cool, actually. What it's doing is it's just doing the same thing as this motor, where half of the motor you can't collect the exhaust because they're facing down in a 2 pattern, and that's doing that twice. We're doing it here, so there's 4 exhausts here we can't collect, and there's 4 exhausts here we can't collect, but we're sharing the carbs, so we get the same exact efficiency. So if you look at the numbers, 301, 1150, 3055, 301, 1150, 3055. It's the exact same motor, but it's repackaged with sharing. So 1/2 of the carburetor turbo bank is doing the same thing in both cylinders. So we lose half. Now, we could throw this carburetor bank back on this side, and then we could throw another set of cylinders on the bottom and double the power, but it's no longer a beam motor because it would be 5 wide. It would still be 3 high, but technically it's just this motor. So I was like, oh, this is still a cool motor because it's this motor that's got a 2 high form factor and puts it in a 3x3x12, and the density goes from 4.76 to 7.41, and it's still the same exact motor, just using sharing. We're just doing it with less parts. And I forgot what the parts, the resource points usage is, but this is way less because we got half the amount of carbs, half the amount of turbos, and it's a pretty interesting, cool little motor. And technically, if you wanted to, you could just copy the top 2 layers of this motor and paste it on the bottom of this motor, and it would no longer be a beam motor or an ice cream sandwich motor or a 2x4 motor or whatever. It would just be a decent mid-sized little motor, which is going to be on the mid-sized motor raft, which is taking a lot of work, by the way. And you end up with a 3,200 horsepower motor that hits like 5,000 across the board. Like, it's a pretty good little motor. It's not the best motor, but because the Beast motor fits in the same exact binding box, but makes 6,400 horsepower, so double the power, but like 1/3 the efficiency. So the design triangle god is appeased. We haven't broken the laws of the design triangle. And then when I was building this motor, I was like, okay, now we got to go to 4 turbos per carb, which I don't have a single beam motor, and I don't even understand why you would do that. And there is ways to do it, but there's not really a use for it. And so I built a little motor to see if I could get 4 turbos per carb and all that stuff. And when I was building that motor, I ended up coming up with this design. And this little thing is so cool, I actually gave it a name, and I called it the Micro Zero. And why I called it the Micro Zero is because it's a zero fuel motor. It's a tiny little zero fuel motor. There's no room for a crank. Well, originally I built it on a crank, and the binding box was 1 taller, and it was making half the power. And so I was like, you know what? I can cut the binding box down by removing the crank, because if you're going with zero fuel motors, you don't care about cost. They're big. They're big compared to the power that they make, and they use a crap ton of turbos, so you're not really worried about it. So I'm going to cut the crank out of this thing and make it a multi fuel and multi core motor. And originally it was only 4 cores, but it was lacking exhaust, and I said, well, can I fit a 5th core in? And I was able to fit a 5th core in and still fit it in the 16 limitation of this raft. So I was able to get a 3x5x15, and I was able to get 5 cylinders in, so I can get 1,000 power out of it with 4 turbos per carb, and it doesn't use a crank, so the expense is going to be up. And since it's 4 turbos per carb, you're not going to get a lot of, and then it doesn't share. I will be looking into this design a little bit more, see if I can do some of the things I did here, repack it with some of these ideas, and see if I could get some sharing on it and get the density up a little bit. But it's 1,000 horsepower and 5 cylinders, so it's no different than these 2 motors making 800 horsepower in, with 8 cylinders. So it's pretty close to the same. Or, I mean, well, this one making 800 horsepower out of 4 cylinders. This one's just making 1,000 out of 5. So it's technically these cores with 4 turbos per thing. And the way I did it was your standard old 3 turbos per carburetor, the same as that, and then I just pasted another one on the back side because you have a 3 wide binding box, because you could fit 3 in a 2x2x2, and so you have the third extra block. We can go out to 3, so we just add another one in, and it was a pretty easy plumb by not putting the non-inline side by side, because a lot of times when you put non-inline here and then a non-inline here, you get trapped when you're trying to do your parallels, your series side, because exhaust will come, exhaust will come in. Where does it come in on this motor? I think right here. It'll come in right here. It'll go to this one. Well, right here. This one will come in and then go here. And then it'll go to the one behind it, and then it'll come down, and it'll be fine to come out here, but then when you come here, you come out, and then you end up coming out like over here, and that's not a good place to be, because you have to come back and collect these some kind of way, and it's always a problem. But just by putting the inlines left and right and putting the non-inlines on top of the carbs, it was a pretty easy plumb, and it ends up being $4.99 at 0 fuel at 10%, $39.88 at 0 fuel, and $19,921 at full load. And I think that's because, if I remember right, it gets exactly 30 exhausts. It's perfectly series paralleled, and it gets exactly 30 exhausts. So this is an exemplary specimen of getting exactly 30 exhausts in the space that I've limited this RAF to in a beam motor. Make it a 0 fuel motor. And when you make 0 fuel motors, you're going to have to give up some power. So 1,000's pretty good for this space. Considering I have a non-beam motor, right? I mean a non fuel efficient motor right here that only makes 800 horsepower in a 3x4x16. This is a 3x5x15 making 1,000 horsepower, and on top of that it's a 0 fuel motor. So this motor is pretty freaking good, but it also exposes a little bit of hypocrisy in ultra efficient motors, that they're stupid. And if you watched my last video, I kind of talk about why they're stupid, because once you get to 0 fuel, there's no more efficiency to be gained. Okay, so I can I can get this power per fuel number up to 70,000. So what? You're still using 0 fuel. You can't increase efficiency past. Efficiency is based on how much fuel you use. You can't increase past that. If I'm using no fuel, you cannot increase. All you're doing is increasing your numbers, which is stupid. You're not gaining anything. And to do that, you're going to have to use more turbos per carb and a supercharger, or a supercharger. And my argument would be a supercharger would be a better way to go, because 5% of 19,921 is still a lot of a gain. But does it gain anything? No, it doesn't. It just brings the numbers higher, and it boosts the low end. So instead of 499, I might be like 800. But still, it's still zero fuel. It's not doing anything. All we're doing is adding superchargers or turbos, and turbos don't just add themselves on. To get a fifth turbo on here, we'd have to get rid of the non-inlines here, which makes this motor really easy to plumb up to have that extra carb connection, which means that these can't be in here. These now have to be inlines, which would be facing up now, and then we have to have a motor inline sticking out the side of here, which makes the binding box 2 higher. Instead of being 5 high, it's now going to be 7 high, and then it's no longer going to be 3 wide. It's going to be 4 wide now. So it doesn't help anything. It's not going to gain anything. We're going to use more turbos. 1, 2, 3, 4, 10 more turbos. We're going to add a crap ton of plumbing. It's going to get stupid complex, and we're not going to gain anything. We're going to lose density. We're not going to gain power. We're going to lose density. We're going to add cost from the extra turbos and all the extra pipes. We're going to add complexity, and nothing is going to be gained. So this kind of shows that this right here, this exact point, this exact motor is the hinge point for diminishing returns. There's no way to go past this motor. The only thing you can do is maybe make this motor share to get more power out of it, to get more density out of it, but you're not going to gain more efficiency. You can't gain more than infinite efficiency. So this shows the exact point of diminishing returns, and that's it for the beam motor raft. And there's a link in the description for this raft and all my other rafts. And once again, if you guys like these rafts, use any of these motors, you learned anything from these rafts, give me a thumbs up on this video, give me a thumbs up on Steam, follow, leave comments, gratitude, tell me what you learned, something you didn't know, ask questions about stuff you still don't understand, and I'll see you guys in the next one.